Hello everyone. Thank you for joining today. And let's kick it off. So, who is Anton? Actually, Frank pretty much covered it all. I'm a developer and I work here at Very Reasonable People. And in my free time, I spend maybe a bit too much time on audio and sound and music because that's just what I enjoy doing. And today I will be talking about visualizing sound on the web platform. So how did I even come up with this idea actually? Because it maybe sounds like strange things to do actually with your free time. And actually not only free time, but also some time at work. So thanks for sponsoring that. So I don't know. Anyone here use Winamp and Windows Media Player?
Sure.
Hey, I like that. And they had this kind of creative, trippy visualizations there. I used to connect them to a beamer and just kind of watch them on a wall. And, and I thought one moment, well, it's actually interesting. How do they actually work? Like, how can you take sound and just turn it into some visual, you know, with changes together with the sound? So I just kind of started playing with this idea. And I thought, well, first I need to understand what is actually sound and what can I visualize about it. And it turns out there are three things. One of them is loudness. And you all pretty much know what is loudness. And yeah, you know, you can go really down or it can become really high. And you know, if you visualize can be a shape which is small then becomes big and it's easy. And then you have pitch. So again, like, I can try to speak with a high voice or kind of with a deep voice, and you know, it changes the pitch of my voice pretty much. And it's again easy. It's either high or is it down. There's nothing special about it. But then there is this third kind of weird one, which is timbre. Because like, if you look up on Wikipedia what is timbre, what they say is, timbre is everything about sound which is not pitch and not loudness. And you're like, all right, so that doesn't really help. So how to actually visualize this sort of thing? And yeah, I have this little example of timbre, and you might think it's a video, but actually it's mostly just audio because you cannot put. Oh, here's my mouse. You can't really put audio in Google Slides. I think that's it. Hey. Okay, what was the first instrument? Piano. All right, and second one?
Cello.
All right. So how did you know that these different instruments? It's same loudness, it's same note, it's A2 note, but yet you know it's a different sound. Well, they have different timbre. So timbre is what makes the sound unique. So how can you go about visualizing it? Well, before we go there, I need to do a little bit of explanation of what sound actually is, because you'll need it. Now comes the difficult part of navigating this mouse thing.
You go all the way to the right.
Yeah, but there it is, no?
Oh, okay.
Okay. So luckily for us, there is a company called Google, and they already did quite some nice visualizations. And actually, they use WebAudio to do this visualization. So you can take an example of what you can do with WebAudio. So what are these blue dots? Well, what they represent here, it's as molecules of air, right? Because what sound really is, these are vibrations in the air. So when I speak, it creates vibrations in the air, which at a certain moment, they reach your ear, and your brain is capable of recognizing this as different sounds. So be with me. So where is mouse, Frank? Frank, can you help me there? Yeah.
Yeah, up.
Yeah.
Little up. Yeah.
Yeah, good enough. Okay. So let's try it out. nothing happening there. Did I just broke Google? Google, hello.
Press the blue button in the bottom right.
No, it's to just play the thing.
When you have a JavaScript, do you have a JavaScript blocker?
No, in this case, no.
Okay, no Google demo. Sorry for that. So basically, what would happen when I press the thing? You would see that these molecules, they start vibrating. And if I play a high note in here, they will be vibrating really fast. And if I play a low note in here, they will be vibrating slower, right? And there is an important term for that called frequency, which is kind of similar to a pitch, but it's a bit different. So when you have low frequency, vibrates like kind of slow, and this means that the sound is low. When you have high frequencies, you hear a high-pitched sound, right? And also what's important to understand, the sound is a wave of vibrations, because like you sit here now, when I speak, the air pressure at where you speak, it goes up and down, up and down, up and down. So if I go up and down, I start visualizing it like this, you got a sine wave, right? So it's up and down, up and down, up and down. Then I start moving in time, you got a wave. And that's what these things were supposed to show you. Now I have to improvise a little bit, but that's all right. So I hope we on the same page now. Sound is a wave, right? Does make sense a little bit?
Yes.
Woo. Okay, thanks Google. Frank, I need to go back to my presentation. I also need to get new glasses. All right. So, sound is a wave, right? Can be a wave like this. But a wave like this would sound like extremely boring, like beep. Well, actually, this one would be more like beep, and this one would be like beep, because this is, this one has lower frequency, this one has higher frequency. But in reality, you will never, for any nature sound, for human voice, for any instrument, you will never see a wave shape like this. They always are much more complex. And this is because they basically are like a sum of a simple waves. So if you take whatever complex sound, anything, you can decompose it into these waves, into really simple waves like this, right? Okay, so let's agree on that. We can take any complex sound and we can decompose it in different components, and you can say, well, this sound has, more bass component and maybe less high component, and etc. So another way to visualize it is do something like this. So it's like a bar graph, right? And it's a kind of, we get very close to actually visualizing a timbre, because depending on the musical instrument, for the same note, you would have different amounts of kind of high pitch components and low pitch components in your sound. And what this bar graph shows, you see, on the right there are high pitch components, and there on the left you are low pitch components. So as you can see, there is more low pitch components in this sound, and this is actually a recording of my voice in here. And if we record some of your voices, it might change. You might actually get more high pitched in here. So this kind of shows us something about the timbre. And from here I will go to my first demo, which, as I will explain, is pretty much based on this idea of taking the sound apart into different frequency components and visualizing them, these components. Okay, let's move. And I called Angry Rays Demo. And I hope for this one we will actually have everything working. Okay. So Angry Rays. For this one, I'll take the microphone so it's okay. No, wait, I actually need music. Music. Loop. Start.
There is a man never say praise. Don't wash his foot, never walk for days. What is born, very for me. Never ever sent, never paid no rent. Only walk up out and begging for stands. Very for me. Never wash his face, never wash his feet. I don't know how we live in, how he does eat. Well,
All right. Can I make the sound louder but keep the image? Is it possible? Like less loud but keep the image? Because I don't have like in here. Or if it's not possible, let's just switch it off then. Where is my mouse? Right. So that was it. Yeah, would have been nice actually to still have it here. But anyway, so you see these lines kind of dancing around. And well, each of these lines was pretty much this line, but it just rubbed them around the circle. And then you also see that they kind of go zigzaggy, the lines. And this is basically based on the loudness. So if the sound is loud, they got really zigzaggy. And if it's less loud, they just keep on straight. And there is also some playing with colors. And now I will show you the code implementation. I will not go into details, and I don't want to actually understand the details. I just want to go with like kind of the main steps of it. So how does it actually work? So first of all, you need to get the audio source from somewhere, right? And for this, WebAudio comes really handy. They provide you with all the capabilities to do that. So what I do here, I'm using just a microphone input. So I'm getting microphone input, but it can also be like from some sound file on the internet. Then WebAudio gives you something called analyzer node. So you can take your audio input, you connect it to this analyzer, and then you can keep asking this analyzer in a loop, hey, give me information about the audio which is playing. So basically, in my case, what I do, I ask, hey, please say to me, you know, what is the number representing each of these bars, right? So yeah, if I have 13 bars, I would get like an array of 13 numbers, and that's pretty much it. So I have this data about the audio, right? And then all that's left is just to visualize it, right? So I pass this data into Canvas. So I have this function called visualize, and this happens on Canvas, and it just receives these audio features, which in this case just an array of numbers and loudness. So going further, here, visualize is really easy. It just gets these numbers, these coefficients, it gets loudness, and it maps them to some visual parameters, right? Because you have audio parameters and you need to represent them visually. And for this, a very handy function to implement is map range. So it's something basically which maps a value from one range to another. Because maybe loudness where range goes from, I don't know, 0 to 1, and maybe zigzag range, I need to have it from 10 to 100 or something like this. So I just need to map it in range. And in here, yeah, it's just a loop which goes through these coefficients and it draws a line on a canvas. Then that's pretty much it. And another hint or a tip is that, well, actually some of these values, they can change really fast. So your visualization will be like really jumpy. So you just need to kind of calculate some average values over time, so it just becomes more smooth and more pleasant to the eyes. And this works actually the last code slide for today, I'm sorry to say that. But moving forward. So I did this, but somehow, I don't know, I wasn't really satisfied, and I got this idea that I want to visualize human voice. So like come up with a visual representation of human voice. So you can take your voice, because each voice is unique, right? Each voice has unique timbre. And what if I can create this image, this shape, which is just your shape. So whenever you speak, I can generate this shape for your voice. Someone else will speak, you get a different shape, right? So that was my idea. And I thought, well, someone must have done something similar in this direction. And I thought, well, what about speech recognition, right? Not the speech recognition, but actually the speaker recognition. So you recognize who is speaking, right? Because to recognize who is speaking, you need to extract some data which describes you as a speaker, right? Some numbers which describe your voice. And then, yeah, you can see, you can just pass these numbers to this visualize thing, right? It sounds easy, right? So let's see. So why is there a fluffy rabbit in here? Does anyone know? This is a rabbit hole. Because this is what speaker recognition really is, you know? You can go to Amazon, you can, you know, get 10 books like this about speaker recognition and just get completely lost in it. But it doesn't have to be. There actually are some quite simple algorithms, and I just took one of them. I found a Python tutorial and implemented it in JavaScript. I mean, it was nothing special about it. And before I go into there, I need to explain another concept called MEL scale. And before I go there, I'd like to do a small experiment with you guys. It's not going to be painful, I promise. Okay. Wait. Okay. Who here thinks that these two sounds were the same pitch? Wow. No one? Oh, that's great. What about these two sounds? Who here thinks these two sounds were the same? Oh my God, what's wrong with you guys? The thing is that, well, as I said, what defines the pitch is basically the frequency, right? So if you have two sounds, you can measure kind of, or just take one frequency, it's subtracted from another, right? So some distance. So maybe first thousand was like 10, second one was 20, so its distance is 10 between them, frequency-wise, right? So the distance between first two sounds and distance between second two sounds was absolutely the same number, all right? However, you perceive first two sounds as different and second two sounds as the same. And this is because human brain is much better at recognizing the difference in sounds at lower frequencies than at higher frequencies. So I played first two kind of low-pitched sounds, and you can recognize them really well. This is one sound, this is another. And I played now two sounds which were more in here, and you couldn't recognize them, because this is how your brain actually works. And this is kind of called psychoacoustics, right? It's actually the difference between frequency and pitch, because frequency doesn't match one-to-one to pitch. It's actually your brain does it differently. And this is why this scale, it's like the previous bar graph I showed you, but you can see that by going in here, you get this wider bars, right? Because you're much worse at recognizing differences in here. So to be able to recognize the difference, you need to make these jumps longer, bigger, wider, you know? Because, you know, each of these bars represents how much of high-pitched, low-pitched sounds are in the sound. So if these two bars, if this bar would be like two small bars, and you say, well, there is this component, it doesn't make sense to make them separate because you can't recognize them, right? So you can as well just make them one bar and say, okay, oh, there is so much, this high pitch, and then, so far. Does it make sense?
Yep.
Okay. So this is the MEL scale, and this is what base for speaker recognition, actually. Okay. Doop. I need to go further in slides. Oh. Okay, so really fast about how speaker recognition actually works. So you take a piece of sound, maybe a piece of speech, and you break it down into very short pieces. So 25 milliseconds each piece, because, well, the way you speak, it changes a lot during your speech, so you have to just analyze it in small pieces. And then for each of these pieces, you calculate these 13 coefficients. So 13 coefficients, they just come from these 13 bars. So each bar is a number, pretty much, right? So if you take these 13 coefficients, they pretty much describe this little 25 milliseconds piece of sound. So you get this, and then there is some dark magic, I like to call it. But actually, it's just some mathematics which does something like a really difficult way to get an average of this, and it comes up with 13 sets of 13 coefficients. Because if you would just take an average, you would just get one set of 13 coefficients, right? Does it make sense? But you actually get 16, and it's called clustering, but it doesn't matter right now. So this 16 sets of 13 coefficients is really what describes your voice, pretty much, right? So if you would want to recognize a voice, what you do, you train your system with audio of my voice, of your voice, of your voice. And for each of us, we just get this 16 sets of 13 coefficients. We store them somewhere. And when you want to recognize it, again, you extract these numbers and you just compare them. And whatever is the closest match, say, hey, this person was speaking. That's how speaker recognition works. It's like nothing magical about it. Just extracting some numbers, comparing them. That's pretty much it. Okay, so at this one I was kind of happy. Like, hey, look, I actually have these numbers. All I need to do is just to visualize them. I mean, yeah, great. And then because if you think about it, what does it mean to have 16 sets of 13 numbers? It means that, well, each of these points has 13 dimensions, right? So how? Not something like this, maybe, I don't know. And I thought, well, whatever, I'm not doing this. So what I did, I just took an average of this and I got 13 numbers. Which is a bit oversimplifying, but for my purpose, it's just good enough. All right. And so now I'm gonna have 2 demos, and this will be the end. Okay, this one. Okay, let's see if it works. I really hope it does. So what do we see here? Well, it's a web app, and you can speak in the microphone, and it would produce the shape of my voice. So, and the shape is based on these 13 coefficients, pretty much. So it represents my voice. And for color, I use some pitch detection algorithm, which is also actually not that complicated if you pick a simple one. So let's try. And it says, say hello, hello, hello. So say something 3 times. It's basically important because you need a bit more data to be able to make it better. And also, well, the thing is that depending on the sounds you say, it also changes this coefficients a little bit. So really the shape is a result of what you say and who says it. Yeah. So therefore, it's important if you want to compare different voices to say the same thing. Okay, so let's try it out. Look. Do-do-do-do-do. Hello, hello, hello. Okay. And let's try another time. Hello, hello, hello. And it's sort of the same, all right? So now, is there a volunteer in the audience who wants to see the shape of their voice? Okay. So when I press, it becomes ready. Just say hello, hello.
Hello, hello, hello. Or should I try it another time?
If you want, yeah, sure.
Alright. Hello, hello, hello.
Anyone else?
Is it on?
I need to press.
Hello, hello, hello. Oh, it's similar.
Yeah, but a bit more bump in there. And yeah, it also recognizes the pitch a little bit. So if I try something like, hello, hello, hello. Then suddenly it became yellow. You know? Yeah. And after that I thought, well, actually I want to make a dynamic shape as well. So, Frank, I need your help again. Frank. Okay, so yeah. And where is this mouse? Here it is.
Yep.
Okay, and I'm gonna change this one to voice shape, and I'm gonna change input from music to microphone. Okay, and let's kick it off. Okay, so it doesn't do anything because I'm not speaking my phone. And now look at it. It starts changing. So it's the same principle as before. So this shape represents my voice, and it just rotates a little bit to just make it look prettier. And it's quite interesting actually that, you know, it also catches some sounds from the audience as well. And again, if I speak high, it's yellow, and if I speak low, it's gonna become orange. Well, thank you. Yeah, guys, that was it. And just for a conclusion, could you, Frank, help me again? I really need new glasses.
Yeah.
And conclusion is extremely brief. It's just a list of resources you can use because we're going to share this presentation. So if something from what I've been saying seems interesting to you, you can take a look. There is my website. There is a link to the demo. There is website of Reasonable People. Thanks for sponsoring. And there is a bunch of just learning resources about web audio and sound in general. So thank you very much.
Great. Do we have any questions?
Yes. Well, wait. We're gonna be professional. Please.
Yeah. I'm always amazed by the app Shazam. Does it also use the same algorithms, like the 16 sets and 13, or is it different?
I'm not sure if they use exactly the same. I think I've heard that they also use Mel scales of the coefficients, but I'm sure that their recognizing and learning algorithm is much more complicated than what I did. Yeah, but you can definitely apply it to music. Yeah, like the one visualization I showed you. Yeah, you can turn on music, and for different music it will look different. Yeah, so it works. Yeah. Okay. Anyone else? All right. Then that's it.
Cool.